Hi everyone. In section 0.7, let's do part D on the test for factorability for quadratic trinomials, QTs. QTs look like this: ax squared plus bx plus c, where a, b, and c are non-zero integer coefficients. So for example, down here, x squared plus 3x plus 2. That's an example of a QT. It's quadratic because it's second degree, and it's a trinomial because it has 3 terms. We're going to try to factor this old school over the integers, meaning that we're going to decompose this as a product of factors where we're only using integer coefficients. We're not using things like 2/3 or pi. Now, before we apply the test, we need to assume that the GCF is either 1 or -1. If the GCF is 2 or 3 or something like that, you have to factor it out first in order for this test to work. Again, we're trying to see if we can factor something of this form into something like this: a factor times a factor, these 2 linear factors with integer coefficients. Now, we're going to introduce the discriminant, which is b squared minus 4ac. This may sound familiar because this does come from the quadratic formula. It's the radicand under that square root sign. And yes, there is a way to use the QF to help factor these things, these QTs. We'll talk about that in chapter 2. But we're going to use this discriminant to figure out if we can factor a QT like this, old school, into this factor times this factor, something like that. Okay, so let's look at this example. X squared plus 3x plus 2. What are the values of a, b, and c? What are the coefficients? Notice that they're all non-zero and integer. All right? What are a, b, and c? It's good to write these down if you're using the QF, for example. Here, a equals 1, that's the leading coefficient. B equals 3, that's the coefficient on x. And c equals 2. That's the constant term here. Bear in mind, if any of these are negative, make note of that. That's one reason why it's good to write these out, or type these out. So let's now work out the discriminant. The discriminant is b squared minus 4ac. So this is going to be, b is 3, and we're going to square that. So 3 squared minus 4, a is 1, c is 2, all right? And if you work this out, 9 minus 8 is 1. The discriminant turns out to be 1. Well, so what? So what? That means that this QT here can, in fact, be factored over the integers. This QT can be factored over the integers, old school, which means that you're not wasting your time with guessing and trying to figure out what these factors are. There's a way to do it. There's a way to break this QT down into something like this times something like this. Hopefully, you don't need this test to figure out quickly that this decomposes as the factor x plus 2 times the factor x plus 1, or vice versa. If you're having trouble with this kind of QT factoring, you may want to practice on Alex. But now, if we had a more complicated QT, where the coefficients were more complicated, like a 42 and a 37 and a 111 or something like that, then could we factor that over the integers? Then the test for factorability could be very helpful. By the way, because the discriminant is 1, why does that mean that we can factor it nicely? Because 1, the discriminant, is a perfect square. It's a perfect square. Perfect squares are squares of integers. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and so forth. So if your discriminant is 0, 1, 4, 9, 16, and so forth, then that means you can factor this QT old school, like so. Something like this. In fact, if the discriminant turns out to be the magical number of 0, then something very interesting happens. If the discriminant is 0, then we have an extra clue as to how to factor this. The QT will factor as a perfect square trinomial. The QT is a perfect square trinomial, and it can be factored as the square of a binomial, meaning that the two factors here are going to be twins. So for example, x squared minus 6x plus 9. If you work out the discriminant, like we did over here, it turns out that the discriminant is 0, which means that if you factor this, you're going to end up with basically x minus 3 times itself, or more concisely, the square of x minus 3. We usually prefer this to this in terms of what we write out. A PST can be factored like so, the square of a binomial. We've seen that before. Now, if the discriminant is not a perfect square, if we get a 2, a 3, a 17, or any negative number, even a -1 or a -4, certainly a -7, then the trinomial is prime over the integers, and we cannot break this down any further. Remember, we're assuming that the GCF was either 1 or -1, all right? And we cannot break this down in a meaningful way, like something like this times this. It's prime. We cannot break this down any further in a meaningful way. The test for factorability. Checking to see whether you're wasting your time or not in trying to factor a QT old school, a factor like this times a factor like that. If the discriminant is 0, then that tells you how to factor. It's going to be a PST, the QT is a PST, and it factors as a square of a binomial. We take the x, we grab the middle sign, the minus, we take the square root of the constant term. The square root of 9 is 3, and that's squared. As I said before, I have here 12 factoring examples for you to look at, and I have solutions later on.